Alright, how you guys doing? I'm going to be multitasking a little bit and eating my lunch while I do this presentation. So, here's the deal. We're going to run through Chapter 2 real quick. Chapter 2 has to do with, we've talked a little bit about this in class already, but it has to do with environmental systems. So, the things are interconnected. You know, we watched the movie The Lorax, and it kind of really shows us how these things are interconnected. So, like, we look at things like, for example, in this here, they're talking about cod, which is kind of interesting because in the state of Massachusetts, we have a place called Cape Cod, and obviously Cape Cod is named for the codfish that's caught here. Actually, this is the codfish you would find in Massachusetts. They're kind of a reddish brown color. You know, there are many species of cod. They all happen to be a bottom fish. There are some other ones that are similar, like haddock or hake or pollock, are all very similar style fish. But the codfish that we think about is we can talk about the fish being a system of its own, in the sense that the actual health of that particular fish. We can then look at how that fish is interconnected with other fish. For example, sea herring. Cod eat sea herring. They actually eat a lot of varieties of things. They eat crabs and lobsters and things like that. But sea herring is obviously one of their things. We can talk about the quality of the ocean itself, as far as temperature, salinity, current, things like that. And then the other thing we can throw in there, we can toss in there fishing, human activity. You know, whether it's people running boats, people actively fishing. What you're seeing here, I'm going to zoom in a little bit. This is called a trawler, a long line trawler. And what these long line trawlers do is they literally they'll have devices on the boat, that sonar devices that'll pick up where the fish are in the water column, from the top of the water to the bottom, and they'll run their nets out, travel at a certain speed, and they'll drag their nets through the water. The bad thing about this, obviously, is you're not targeting one type of fish. They're catching whatever happens to swim inside the net is what they catch. So the interconnectedness of this is, if there's too much trawling going on, you're not going to have enough codfish. If there's too many cod, the herring numbers might go up. The issues with having there is a sense of having too many of one species in an area, because it become overpopulated, which can then cause that fish to be not as healthy. You have a little less of that in the oceans than you do on land, but there's this interconnected piece of all these organisms. I'm not going to run through the vocab. I'm going to skip through that. You guys can do that on your own. I do want to talk a little bit about some chemistry. So most of you have had a year of chemistry before you've come to see me. So this is showing you, this is methane, CH4. The carbon is the black one in the middle, and the hydrogens are these ones on the outside. Okay, so methane, CH4, makes this kind of they call it a tetrahedron, or triangle shape. But what I want you to see with this is that during, we're talking about, you know, elemental things. In this case, this is a compound called methane. There are bonds that take place between them. These bonds are what hold these atoms together. So, for example, this atom of hydrogen is physically stuck to this atom of carbon through this covalent bond. It's the sharing of electrons. So what's happening is, if you look at these orange dots, which are the electrons, hydrogen brought one to the show. So imagine that one of each of these in the pair belongs to hydrogen, and one of each in the pair belongs to carbon. So let's have a chemical bond. Well, we can also have ionic bonds. Covalent bonds such as this, very strong. When you're sharing electrons, tends to be very strong. Ionic bonds are formed when elements form plus and minus ions. Think of salts. You take salt, you toss it in water. The water causes the salt to dissolve, and you get separate sodium and chloride ions. When you have ions, plus and minus, sometimes we refer those as electrolytes. Some of you that are starting sports today, you're going to find this out the hard way, that even if you hydrate, if you don't have the right electrolyte balance in your body, you get cramps. In this case, for us as humans, sodium-potassium pumps, or sodium-potassium, are two of those important ones. In this case here, with ionic bonding, you have two chemicals. You have sodium on one side, chlorine on the other. And instead of there being a sharing of electrons, sodium actually gives up one of its electrons to chloride. And what ends up happening is, each of these new atoms then have the correct or full outer valence shell of electrons. Because sodium lost something that was negative, it becomes more positive. because chlorine creates something that was negative, it becomes more negative. And these two stick together like magnets, so this plus-minus attraction. This is where we get ionic bonds. These ions are what cause muscle contractions, nerve impulses, things like that. So they're very critical to have in the right concentration and the right numbers in living systems. Another type of bond is called hydrogen bond, super weak type of bond. One of the easiest way to break a hydrogen bond, let's say for example in water, is to heat it up. When you heat water up, it boils, causing the bonds to break. Here's kind of an idea. This shows you what a water molecule would look like. Here we have our oxygen and two hydrogens to make the H2O. We can see they're sharing electrons, not stealing. And then notice that each of these water molecules is attracted to one another. So notice that the oxygen on one is attracted to the hydrogen on the other. Here's an oxygen attracted to a hydrogen to an oxygen, hydrogen to an oxygen. These are hydrogen bonds. These are weak interactions. There's no sharing of electrons. There's no stealing of electrons. It's the fact that they have these little tiny charges on the ends of the molecule that cause them to stick together. This is why when you pour water on the table, it puddles together. Or why if you take a glass and you're pouring water into it and you overfill it, it actually has that little bubble above the top of the glass. Properties of water. I'll let you read these as you go. Once again, this is just kind of a quick recap of some of the topics that you've sort of seen before. Capillary action. Think about when you take a spill water, put a paper towel next to it, and the water is wicked or pulled into the paper towel. That's capillary action. Surface tension allows something like this to happen. So this is a water strider or some type of a water bug, and because water binds to itself, it creates this tension on the surface, and things like this little water bug that one are very light and two can spread their weight out across a bigger area can actually physically walk on the water. A couple of huge properties of water. Obviously, if we're talking Celsius here, boils at 100, freezes at 0, or if we're talking Fahrenheit, it boils at 212, it freezes at 32. One of the other things with water is that from a freezing standpoint, as far as I know, it's the only compound on the planet that when you freeze it, it gets smaller. Everything else, it gets bigger. When you freeze steel, when you freeze concrete, everything shrinks usually when it freezes. Not water, it does the opposite, which is why we have ponds, rivers, streams that when they freeze over in the winter, the life is still the life is allowed to live under there, which is kind of interesting. If water froze and sunk in the wintertime, it would actually kill everything that would be in a pond, so we would have never evolved, seeing that we evolved from things in the water. Let's see here. Sorry, just being like a pop out and pop back in, throws up a little bit. Okay. So once again, this is showing you water that's of a frozen variety. Notice the amount of space between it. All right, so you get that space between it, which causes it to be lighter, as opposed to water of a liquid variety. Notice there's less space. More compact, it's heavier. Less compact, it's lighter. Acids and bases. So we'll talk a little bit about this as the year goes on. We'll refer a lot of this to acid-base chemistry in rainwater, things like that, ponds and rivers and streams that become acidic or basic due to pollution. So there's a fine line. Sometimes they use the term like the Goldilocks effect. So there's a fine line between what's too acidic and what's just right from an acid standpoint, and the same thing with base. So most organisms can only live in pHs of close to 7. Usually they can't live too much higher or too much lower than 7. As pollution either rains down as acid rain or runoff from factories or homes or any type of industrial setting, as rivers, streams, and ponds become more acidic or more basic, and they move away from that pH of 7, which is right here in the middle, the neutral. What happens is that the organisms that are not as tolerant to the changes die off. So, for example, you might find that half of pH level change in a body of water might be enough to kill off more than half the organisms. Now, you say, well, it gives the organisms that are left more space, and maybe they're more tolerant and have that ability to survive. but it also lowers the genetic diversity. It also lowers the biological diversity. So I'll use an example. There's actually a question we're going to look at from the AP exam that shows you, 10 different species that live in a pond, from fish to insects, and what they do is they sample the pond at different pH levels around the pond, because sometimes there can be pockets of pH change in ponds based on like what houses are near them, what businesses are near them, things like that, what water flow comes in. And so what they would find is that in places that there was more acidic or more basic, you had less species living there. You had plenty of the species that was tolerant. So let's say you had 10 species of fish or living in a particular pond, and when you went to a place that was more acidic, maybe only 3 of those species existed. There were plenty of fish to go around, but the fact it went from 10 to 3 species really made a big difference. So obviously here are bases, here are acids. 7 is pure water and neutral. This would be like distilled water. Every time you make a jump, so the pH scale is logarithmic and it's log base 10. Excuse me. This means that a jump from 7 to 6 is an increase of 10%. And a jump of 6 to 5 is an increase of 10%. If I jump from 7 to 5, it's 100. It's 100 times increase. So it's 10 times 10 or 100. Think of things like we'll use cola. So soda is actually very acidic. So compared to pure water, it's 10, 100, 1,000, almost 10,000 times more acidic, right? Which is why it's really not good for you. I had a kid former student do a science fair project years ago, and he took a couple of his baby teeth and he soaked them in different types of soda, and it actually caused the teeth to actually disintegrate. It's crazy. All right, so once again, we just discussed this real quick. Another example of the pH scale. Water tends to be rainwater tends to be slightly acidic, which is fine. Notice that it takes a pretty big jump. So you're talking for a lake affected by acid rain, so you're looking at a 10, 100, 1,000% increase in order to get that big change like that. Let's see. A couple things with well, I'm not going to spend a ton of time on this, but what I do want to talk about is let's take a look at this picture here real quick. So this is a site you might see naturally happening in forests. Forests do catch on fire. Fire is actually good for the forest in some respects, especially naturally occurring fires. It burns up the low-lying brush that's there. It also, as the organic matter, in this case the trees, burn, it actually adds nutrients back into the soil, which allows more things to grow. So there is this constant fires that we have in forests, but if you look at what's going on out west, we don't want to see quite that. But you do want to see natural burns are actually a pretty good way for forests to kind of recoup nutrients into the soil. So again, we're freezing here a little bit. We'll get there. And there's a copy of this for you guys as well too. So some biologically important molecules. They use the term organic compounds. Anything that has carbon, hydrogen, oxygen, nitrogen, we consider organic compounds. Some of the major things that we'll look at there when we talk about this. We'll talk about this with regards to food. Carbohydrates, proteins, nucleic acids, lipids are all things that are found in our foods. All of these things, at one form or another, actually come through plants. So we're very plant dependent. Even if our diet is not completely made of plants, like my salad here, we're still dependent on those plants to produce these compounds for us. We'll talk about cell structure. Obviously, this is some stuff that reared its head when you were in biology. We'll talk about single versus multicellular structures. So you can determine the health of some aquatic areas based on the types of wildlife that you see there. For example, here we have this is some type of euglena. It's a single cell organism with a tail, as opposed to a multicellular. This would be kind of like some type of water lice or mite or something like that. It's a multicellular organism. We'll get into talking about calorie and calorie counts, what all those things are. We'll get into that. We'll get into a little bit of food sources and those kind of things. We'll talk about forms of energy. Obviously, some of these you should know already. Kinetic and potential. Kinetic is energy in motion. Potential stored energy. Chemical energy stored in bonds. Here we see potential energy behind the dam here with the water. kinetic energy as the water moves down through the dam. We'll talk about thermodynamics, the fact that there are inputs and outputs. Car is a perfect example. Car burns gasoline. That gasoline then helps propel the car forward. There's friction between the tires and the road. There's friction inside the engine, which causes heat. So the majority of what goes into the car actually does not actually move using the forward motion. A lot of it is actually lost due to energy transfers. The bigger car you have, the less efficient it is. The less efficient it is because it has more mass. We'll talk about a few more types of efficiencies. We'll talk about the fact that factories that produce electricity send it through wires and then ends up into your home. Ironically, it's only 1% efficient to actually turn a light bulb on. The majority of the efficiency, if you notice, is lost right here is heat. Traditional light bulbs only produce 5% light and 95% heat. LEDs and compact fluorescent light bulbs are actually fixing that problem for us. So if you upgrade those in your home, we can get that efficiency much higher. Once again, there's traditional fireplaces. Once again, talking about how heat works. If you have a fireplace, they're really cool to look at. They're great. They give you tons of heat, but a lot of the heat goes right up through the chimney. It's not trapped or stored. A lot of these modern wood stoves, pellet stoves, actually allow you to trap the heat in a more efficient manner. As far as that goes, I'll talk a little bit about steady state. So the idea behind the steady state here is that if you notice this bucket here, right? So there's a bucket, so there's 10 liters of water in there. There's water coming in, water coming out. The reason they consider it a steady state is because the water volume overall is not changing. You start plugging some of these holes, what's going to happen is that the water will actually spill over. It will not be in a steady state. There's too much input, not enough output. If I drill more holes in the bottom of the bucket, vice versa will happen. If I don't turn the water flow up, the water level will actually go down. This is part of our issue with water use in this country, is if you think about the lack of rain, yet we're using it at the same rate, it's not really in a steady state. Okay. We talked a little bit about population a little bit. Increased population, there are more births, which causes more population increase. We can talk about a negative feedback loop here, which is if there's less evaporation, there's going to be less rain. Less rain means the water levels go down, which makes the problem even worse. So take a look at these. Let me know what you think. If you have any questions, by all means, shoot me an email.